All right. Hello. All right, so in the previous lecture we looked at some energy considerations. We determined a few facts. First of all, an assembly of charges, a configuration of charges has a certain, all right, an assembly of charges has a certain potential energy. Okay, there's a system of charges, they are configured in space, they lie at certain distances amongst themselves, so there's a pattern of charges, and we can associate it with that pattern of charges a potential energy. So with each configuration of charges, which is a nice way of saying a pattern of charges, we can associate an electric potential energy. And associated with the configuration of charges, there is an electric field. So these two aspects, the configuration of charges and the electric fields, they are one of the same thing. If you know the configuration of charges, you can use Gauss's law or you can use Coulomb's law to find out what the electric field pattern looks like. So saying that we have a configuration of charges is the same as saying that we have an electric field distribution, and energy is inside the electric field. Okay, and that electric potential energy is the amount of energy that you've already spent in assembling that configuration of charges. Now let's consider a capacitor, two plates, a parallel plate capacitor, and I will not repeat this statement that whenever I say a parallel plate capacitor, unless I note otherwise, these are infinitely sized sheets, okay, or the spacing between these plates is really small as compared to the size. Alright, so this is what I'm talking about, an ideal capacitor. Suppose these plates are separated by a distance capital L, a positively charged plate, and here there is a negatively charged plate. The system as a whole is neutral, which means that there is a charge of plus Q distributed evenly on this plate and a charge of minus Q distributed evenly on this plate. Now these plates are separated by distance L. Now if you look at one of the plates, say if you look at the negative plate and look at the material that makes up this negative plate, then this plate is being attracted by the positive plate. Okay, so energetically it would be favorable that this capacitor does not exist. In other words, that this plate should rush towards the positively charged plate and coalesce with the positive plate. Alright, because the positive and the negative charges are attracting one another. So if I would like to calculate the electric force on this plate, what would be the direction of this force? It's towards the left. Now Fe represents the electric force on the negative plate due to the positive plate. Now could you please determine what the magnitude of this electric force ought to be? Could you please work out the magnitude? Hello. So we are interested in determining the magnitude of this electric force on the negative plate. So one has to determine the electric field on the negative plate that is caused by the positive plate.
if you use direct Coulomb force?
Yeah, it's the Coulomb force. Could you calculate this force in terms of the electric field, please? I'd like to see the force in terms of the electric field. This is incorrect. It's incorrect because you cannot define a distance between a positive and a negative. There are different distances. This is incorrect. Most students would write something like this: 1 over 4 pi epsilon naught q squared divided by L squared. But let me tell you, this is incorrect, because you cannot define an L. L, in Coulomb's law, there are negative charges and there are positive charges everywhere, so you cannot define an L. If you were just looking at the distance between two charges, the distances are all variable. So this is not the proper way of finding the electric field, of the electric force. You need to determine what's the electric field here. And the electric field is constant all along the length of this negatively charged plate. Yes?
Sigma और epsilon naught Q.
That's the electric field.
उसको Q से multiply करने का force आ गया.
सही. What's the electric field here? Sigma over epsilon naught. So what's the force that acts on this plate? Q times this.
If you use QE,
All right. So this electric force Fe is, let's look at its magnitude. The electric field at the position of this plate is constant all along the length, because these are infinitely sized plates. It's sigma over epsilon naught, where sigma is the uniform charge density on either of these plates. So this is the electric field at the position of this plate, and we have to multiply this electric field by the charge. So the total charge on this plate is Q. And in order to take into account the direction of the electric field, I put a minus sign here with an iota. Okay? Where my axes are defined like this. This is my x-axis and this is my y-axis. Now this is the total electric force that acts on this plate. And the action of this electric force is that it would try to accelerate the negatively charged plate towards the positively charged plate. So there has to be something inside the system that is preventing this acceleration. There is some external agency or some energy somewhere that is buffering this acceleration towards the left. Now where is that energy residing? Of course there is no external agency, there is no engine that's running. This system is isolated from its environment. So there must be energy somewhere that is preventing the fallback of the negatively charged plate. Likewise, there is some energy that is preventing the fallback of the positively charged plate. So there is some kind of hypothetical medium in between that is resisting these forces, because this electric force will result in mechanical motion of the plates. So where is that energy? That energy is actually inside the electric field. Because when this capacitor was formed, a positively charged plate was lying here and a negatively charged plate was moving towards the positively charged plate, and then it stopped at a certain distance L. So there is something that has gone into the system which is preventing this downfall, which is preventing the coalescing of the two plates. And that energy is present inside the electric field. Alright? Now, alright, so there is some energy somewhere that is holding back the coalescing of the plates. Now let's suppose what I'm interested in is that I would like to expand this this capacitor. I would like to increase the distance between these plates. Suppose I'm interested in doing that, which means I have to apply some external energy. Okay, because this electric force is pointing to the left. If I would like to keep this plate fixed, and if I would like to move this plate away from the positively charged plate, I will have to apply a force that is opposite to this electric force. I have to hire an external agency to do some work. Okay? Because what the electric effects are dictating is that this negatively charged plate should actually move towards the positively charged plate. But it's being held back by something. And that is the energy stored inside the field, as I'll show in a minute. Now suppose I would like to move this negatively charged plate away from the positively charged plate. This means I have to apply a force in the opposite direction. Suppose I apply a force in this direction, and I call this force that I apply force me. Okay, it's my force. It's the force applied by an external agency. Now what I want is that this process is adiabatic. The force that I apply is just a tiny little bit greater than the electric force, so that I just slowly move this plate away. It's just a tiny little bit higher, so that this force is a tiny little bit higher than the electric force, so that this plate slightly moves towards the right. And I have to spend energy in doing so, because I'm going against the electric field. I'm going against the electric work, against the work done by the internal forces. So I have to apply an external force, which means I have to do some external work. Alright? Now suppose I move this plate through a distance delta S. So in each stage of my motion, I apply a force that is only a tiny little bit greater than the electric force. The electric force, as you will notice, is constant with distance. So I apply a constant force that is only slightly greater than the electric force all throughout this motion. So what I've started off with is two parallel plates that are at a distance L in between them, and apply a force F me that is only a tiny little bit greater than the electric force. The electric force is always constant, so my applied force is just somewhat higher than the electric force, and I end up in moving this plate to this new position where this distance is delta S. So this is the positively charged plate, and this is the negatively charged plate. Of course I have done some work. I have done some work because I have applied an external force, and the direction of the force that I have applied, F me, is parallel to the displacement. So some work has really been done. So when I do work on this system, it increases its energy by the work energy principle. Where is that energy going? It's not heating up the plates, because the temperature of these plates is still the same. That energy must go somewhere. There's no friction involved, so it's not overcoming any friction. The energy that I put in, the fuel that I've burnt, must manifest itself by conservation of energy in energy of some kind. I would like to see, where is that energy going? Yes. सवाल पूछ रहे हैं आप, ठीक है? तो वो एनर्जी कहां जा रही है, हम वो देखना चाह रहे हैं. Let's find out the total work that I've done. Work me. The work that I've done is the force that I've applied, F me, dotted with some ds integral from this position to this position. Both of them are parallel, so I can just write F me into delta S. Okay, and what is F me? F me is just a tiny little bit higher than the electric force. So F me is simply sigma over epsilon naught Q. This is the force that I have to apply into delta S. So this is the total work that the external agency has to do. Alright? समझ आ गई? ये clear है ना? Alright. Now what is Q? Q is the total charge on the plate. If I like to replace this Q by, okay, I can replace this sigma by Q over the area of the plates. So I can write Q square epsilon naught area delta S. Okay? So from here I go here. I want to economize the use of the blackboard. So I go here, Q square epsilon naught A. I put in a delta S according to my own desire in the denominator. If I put a delta S here, I would like to put, alright, instead of putting a delta S here, let's put an A here. So I put A square. So I put A square here. Here I would also like to put an extra A into delta S. So this is the work done. This work must go somewhere because energy has to be conserved, and since there are no other obvious reasons how this energy can go up, the temperature doesn't go up, there's no friction, this energy must reside somewhere in the system. Okay? So let's call this is the increase in the energy, right? Some kind of energy, U. It's not kinetic energy because once I move the plates they remain static where they are. So it's some kind of potential energy that's going up. And that is electric potential energy, because I'm doing work, I'm assembling a new configuration of charges. Okay? I'm making a new system, I'm assembling a new system, I'm inputting extra energy, and that energy is manifesting in the increase of the energy of the system, which is the potential energy of the system, and that is residing inside the electric field. So this work that I've done manifests, appears as the increase in potential energy of the system. Now what is A times delta S? A times delta S is simply the volume. Alright? So, and what is Q over A? It's sigma. So I can write sigma squared epsilon naught into volume. This is delta U. This is the work that I've done. Now if I were to express this in terms of the electric field, my electric field in between these plates is E, which is sigma over epsilon naught, which means that my sigma is epsilon naught E. So the increase in the potential energy of this system, which has been affected by myself pushing one of the plates away, is given by 1 over epsilon naught sigma squared, which is epsilon naught squared E squared into the volume. And this is the increase in the volume. Okay? This is the increase in the volume, because this term is just the increase in the volume. Okay? So let's look at this relationship. What this relationship tells us is that if I increase the volume of the system, that is, the plates move further apart, the volume over which the electric field exists is increased. Now if I have two plates here, the electric field is still sigma over epsilon naught. If this carries a charge density of plus sigma and this plate carries a charge density of minus sigma, this is the electric field. Now if I have plates that are further apart, and these plates are again infinitely sized, and plus sigma is the charge density here and minus sigma is the charge density here, then the electric field will still be sigma over epsilon naught, no matter what the separation between the plates is. But the only difference is that this electric field is now spread over a larger volume. Okay, so the total energy in this system will be higher. If I have a higher increase in the volume, the change in the potential energy will be higher. So having two parallel plates and making them go further apart means that you are storing more energy in the system, because the volume over which the same electric field is spread is higher. Okay, so what we can define is the energy stored in a capacitor, which is the energy actually stored in the electric field. Energy inside the electric field per unit volume. And what is this equal to? What's the energy stored per unit volume? It's just going to be half epsilon naught E squared. And I can denote this energy per unit volume inside an electric field by small u. Oh. क्योंकि गलती हम सब ने कर दी है. Now when we were calculating the electric force on this plate, we need to find the electric field due to this plate. Now what's the electric field due to this plate? Is it sigma over epsilon naught? No, it's sigma over 2 epsilon naught. You just have one plate and you want to find the electric field due to that plate, it's sigma over 2 epsilon naught. Alright, so the electric field at this position due to this plate, when we find the electric field, we discard what this charge is. The electric field is independent of the charge that's placed here. So you want to find the electric field here, due to this distribution of charge, it's sigma over 2 epsilon naught. Okay, so this is a mistake that I made here. It's sigma over 2 epsilon naught everywhere. All right. So any confusions up to this point? So this is the increase in potential energy. Now that there is an electric field inside the parallel plate capacitor, that electric field is given by sigma over epsilon naught. It's not given by sigma over 2 epsilon naught, because now we're considering the field inside the capacitor. So this is sigma over epsilon naught. Sigma is epsilon naught times E. I insert this value of sigma in here. I get epsilon naught square E square. This 2 appears here. Okay, so I'm left with the 2 here. नहीं समझ आई? नहीं समझ आई ना? किसको नहीं समझ आई? Okay. Let me repeat the argument. I am a point P that is at a certain distance with respect to a positively charged plate. What's the electric field at this point? आप बताएं. It's sigma over 2 epsilon naught. Use Gauss's law. I draw a cylinder that extends to both sides. This area is A. The electric field here will be equal to the electric field here. So the electric field here is E multiplied by A. This is the flux passing through this surface. The electric field here is also E. And the area vector is now pointing in the opposite direction. So the flux passing through this surface is also EA. And the charge enclosed is the charge enclosed in this area, which is sigma A. This gives me the electric field sigma over 2 epsilon naught. So the electric field due to one positively charged plate is sigma over 2 epsilon naught. Okay. Now in a capacitor, what I asked you, you have a parallel plate arrangement, a positively charged plate and a negatively charged plate, and you were asked to determine the electric force on this negatively charged plate. So what you did was you determined the electric field here just due to this positively charged plate. The electric field at this point is only due to this positive charge. So what you could do, you could break up this charge distribution into small segments. Each carries a charge dq. The electric force on this small segment is just due to this distribution of charges. So it's one plate which is producing the electric field. So that electric field is sigma over 2 epsilon naught. So this is the force on this segment of charge. And if you would like to calculate the total force on this plate, you just integrate this over this area, and you would get sigma over 2 epsilon naught into the magnitude of this charge q, which happens to be the same as the charge on this plate. So there is a factor of 1 over 2 here. Alright? Now, do you all understand what's going on? अभी भी किसी को समझ नहीं आया?
Sir, how you went from sigma over epsilon naught to sigma over epsilon naught.
Alright. Now here we've used sigma over 2 epsilon naught. Okay, because this is the electric force. This appears in the electric force. Now what I've done here, I want to replace this sigma. I want to replace the sigma that appears here by the real electric field that's inside the capacitor. Okay, now I have made this capacitor. There exists an electric field inside this capacitor. Okay, I know the surface charge density on either of the plates. I can determine what the electric field inside the capacitor is. The electric field inside the capacitor is now sigma over epsilon naught. I had a factor of 1 over 2 because I was just computing the force on one charge due to one plate. Okay, I wasn't considering the entire capacitor. I was considering just one plate and how much force does this positively charged plate influence or cause or exert on the negatively charged plate. So I just had to take into account the source charge, negligible distances. Then this force that you need to apply is actually just almost equal to the electric force. So this is just on the verge of equality. And this is the concept of asymptotic limits in mathematics. You just apply a force that is only slightly greater so that the system remains in equilibrium. Okay? मुझे खुशी होती है जब पीछे से कोई बैठा हुआ सवाल पूछता है, लेकिन आप पूछ लें, चलें, कोई बात नहीं.
Sir, you said that in case of these two capacitors, the electric field would be the same. So this means that the electric force would also be the same, acting on each plate.
Good question. If I just consider this plate and I would like to find the force exerted on this plate, will this force be the same as the force exerted on this plate? Yes, it's going to be the same. If the charge densities are the same, then the electric field here is the same as the electric field here due to either of these plates. So the force on this plate is the same as the force on this plate. Remember that if you have an infinite sheet of charge, the force or the electric field doesn't depend upon how far are you from that infinite plane. Okay? So the force on both of these plates is the same. And these are the kinds of questions I will ask in exams and quizzes. Alright, now any more questions? Because we really need to be clear about this. Anyone else? The slope of this line is simply the negative of the electric field. Okay? So delta V over L is minus E. The slope is negative, so the electric field is positive. It's pointing from small values of x to large values of x. It's pointing in this general direction, in the direction of increasing x. The slope is negative, the electric field is the negative of the slope, so it's pointing in the positive direction. So everything is consistent here. Okay? There's no inconsistency whatsoever. Now if I look at this equation, and I'm only concerned with absolute values, delta V. Okay? This equals EL. Now what is this electric field? This electric field is sigma over epsilon naught. Okay? What is sigma? Is Q over A L. Alright. Now what I have is, if I take Q as the subject of this equation, I can write Q equals delta V into epsilon naught A over L. Which is showing that there is a direct proportionality between the charge that is stored on either of the plates. Either of the plates stores the same amount of charge. One is positive, the other is negative. And it's proportional to the potential difference that has been applied between these plates. Now how do you apply potential differences practically? By a battery, by some power source. So you connect this to the positive terminals of a battery, you connect this to the negative terminals of a battery. If this is V0, then the potential difference that is set up is V0. So this is an external stimulus that pulls up the plates to the respective potentials. It keeps the potential difference between these plates to be V0. Okay? So if you go around this path, this is a closed path in space. The total change in potential should be 0. So here you're going from a positive to negative potential, you're going from EL to 0. And here inside the battery, you are going uphill. You're going from a lower potential to a higher potential. So the potential difference in the complete round trip in this circuit is still 0. And the point I would like to make is that the charge is proportional to delta V. And here you have a factor that only depends upon the geometry of this capacitor. How big are the plates? What's the overlap area between the plates, and how far are they apart? Even though putting the plates further apart or closer together doesn't change the electric field, it will change the amount of charge that is stored on the plates if you apply a constant potential difference. So this geometrical factor, and it also has a contribution from the medium. Epsilon naught is the medium that is in between these plates. In our case it's vacuum or air. So this factor is called the capacitance. And it is determined by the geometry of the system. So my relationship can be summarized as Q equals C delta V. Now I have one question for you. Suppose I have a conductor here. It's a metal. It carries a charge plus Q. And enclosing this metal, it's a 3D volume. Outside this metal there's another volume, like a ring. So this is metal. This is vacuum or air, and this is metal. Now how is charge distributed on the outer conductor? How will charge be distributed? आप बताओ जी.
चार्ज इसके जो मेटल जो है वो पॉजिटिव है ना, तो आउटर सरफेस पे ये नेगेटिव.
किसके आउटर सरफेस पे?
मतलब जो मेन शेल है उसके इनर सरफेस पे.
उसकी तो एक ही सरफेस है.
नहीं, ये अंदर मेटल है ना.
हाँ
ठीक है. और आपने बोला बाहर रिंग.
जी जी.
ठीक है. तो वो रिंग के जो इनर सरफेस है उसके ऊपर नेगेटिव साइन.
नेगेटिव कितना?
माइनस क्यू.
ठीक है. और आउटर सरफेस पे?
आउटर पे उसकी वजह से
if the outer surface is neutral.
हाँ तो वो क्योंकि इनर सरफेस पे माइनस क्यू वो जनरेट करा रहा है तो उसकी वजह से आउटर सरफेस के ऊपर वो प्लस क्यू.
ठीक है. So according to the gentleman, this charge that is distributed on the inner surface is minus q, and if this outer surface is neutral, the charge on the outer surface will be plus q. Okay, because the outer surface is assumed to be neutral. Now this arrangement, does this qualify as a capacitor? Why not?
It can, because there is a potential difference between the two.
And it can store charge. This arrangement also qualifies as a capacitor. There's nothing special with a parallel plate capacitor. A capacitor is just, it shows you that there is some medium that holds charge, and you can use that charge later for good purposes. For example, you can light a bulb through that charge. You can do useful work from that charge. A capacitor is just a charge storage device. So this weird looking system also qualifies as a capacitor, because here you have an island of charge. All of this charge plus q is on the outer surface, by the way, of this inner sphere, and this outer shell has minus q on the inner surface. There exists an electric field between this volume and this shell, and if I would like to plot the electric field lines, they will always be normal to the surface of the metal, and they will be normal to the surface of each metal, like this. They will not be radial because this is not a sphere, but they will always be normal to the respective surfaces. There exists an electric field in this annular region, and there exists some energy associated with this electric field, and that energy per unit volume is given by half epsilon naught E square, whatever the measure of that electric field is. Remember, this formula applies to electric fields of any kind whatsoever. If you're far away from any known object that is of any importance, that is, you're in the outermost expanses of space, and there's electromagnetic radiation passing through space, like the radiation coming from some distant sun or star, then that electromagnetic radiation is also an electric field. There's no capacitor involved over there. That electric field also stores energy. There is energy that is accompanied by the electric field. Every electric field has energy in it. In other words, the electric field can do useful work. Electromagnetic radiation can do useful work. If you have a solar panel and electromagnetic radiation falls on it, it can twist the panel. It's called radiation pressure. So this formula applies to electric fields of any kind. Whenever you have an electric field, you take the square of the electric field, multiply it by the permittivity of free space, divide by 2, you will get the energy density, the energy per unit volume inside that electric field. So now you can think of the electric field as being a reservoir of energy. Okay? It's simply a reservoir of energy. It holds energy. Okay? Now this also qualifies as a capacitor, because there's an electric field, energy is stored inside this capacitor. You can do many useful things out of this energy that has been stored. However, if I would like to dump more charge on the outer shell, suppose I don't want to keep it neutral, I have some charge 4q that is on a metallic sphere. I have built up charge on the metallic sphere, for example by touching it with the Van de Graaff generator. I put some charge on this ball and I connect this ball with the outer shell, so that this shell and this sphere are at the same potential. Charges will redistribute. So now what is the total charge on the inner surface? It's still minus q. Alright? And all the charge, extra charge that has been built up will go on the outer surface. I don't know the amount of charge because some of the charge will be on this sphere, but it will definitely be greater than plus q. So on a whole, this shell will be positively charged, but still the inner surface holds the same amount of charge minus q, and it has the same potential difference between this shell, between this object and this shell. So the amount of charge that is stored on the capacitor doesn't change. In other words, the electric field inside the capacitor doesn't change, because the electric field is only determined by the charge that's on the surfaces. So even though this object as a whole is storing a different amount of charge overall, it's the same capacitor as before. Dumping in more charge on the outer shell does not change the capacitance of this system. It still holds the same amount of charge, which is plus Q, and the same electric field exists in this annular region no matter how much charge you build up on the outer surface. However, if I have an external conductor outside this region, then the capacitance will change, because the electric field outside this arrangement will change. Okay? Because now there is more charge inside, the electric field in this region is going to change. So when the electric field is changing, the total energy stored inside the electric field in this region is also going to change. Okay? Any questions on this point? जी अंदर फिर भी कोई फर्क नहीं पड़ेगा, लेकिन हम इस ऑब्जेक्ट और इस ऑब्जेक्ट को बतौर एक कैपेसिटर के लिए लेंगे. ठीक है, अंदर कुछ फर्क नहीं पड़ेगा. Now I would like to explore a few examples of capacitance. Suppose I have a charged sphere, could be metallic, could be insulating. The radius of this sphere is capital R, alright, and it holds a charge plus Q. Does this single sphere qualify as a capacitor? There is no neighboring conductor whatsoever. Does it qualify as a capacitor?
The charge is on the surface or inside?
The charge could be on the surface, it could be inside the volume, anywhere. Does it qualify as a capacitor? Can I call this system to be a capacitor? Why not?
But if the charge is inside,
There is no charge separation.
There is no charge separation. There is no potential difference between any 2 points on the surface. So the entire volume is an equipotential surface, so everything is at the same potential. There is no charge storage. There is some charge storage because there is some charge Q that has been built up on the surface, but you're arguing that everything is equipotential. Any more ideas?
Considering that the sphere is uniform in surface because edges interacting.
जी, तो ये कैपेसिटर के तौर पे काम नहीं कर सकता. All right. Now, outside this sphere, what's the electric field going to look like? It's radially outwards. So let me draw this electric field. Inside it's 0 if it's a metal. Outside it's radially outward, like the spokes of a wheel. Alright. Now there is some electric field. Doesn't this electric field store some energy in it? It must store some energy in it. Alright. So the consensus in this class is that this object on its own, a sphere that is isolated from everything else, cannot act as a capacitor. But let me draw another surface that is concentric with this sphere. Another shell, a spherical shell that has its center, the center of this sphere. And let me draw this sphere here. It's a cross section of the sphere. And suppose it's metallic. Will the electric field change? आप बताओ, अब हमने एक स्फीयर के इर्द गिर्द एक और बड़ा स्फीयर रख दिया जो कॉन्सेंट्रिक है छोटे स्फीयर से. अभी जो इलेक्ट्रिक फील्ड है इस एनुलर रीजन में, विल इट चेंज फ्रॉम द प्रीवियस केस? आप बताओ, व्हाइट शर्ट में आप बताएं जी. नहीं बदलेगी, इलेक्ट्रिक फील्ड नहीं बदलेगी. इट्स स्टिल गोइंग टू बी रेडियली आउटवर्ड एंड इट्स गोइंग टू पॉइंट फ्रॉम this sphere to the outer shell. Now does this qualify as a capacitor? Okay. Now if I were to move this outer shell further and further away so that it goes to infinity, wouldn't this system still qualify as a capacitor? It will. Having this outer shell that is concentric with the sphere doesn't change the electric field at all. So if this is a capacitor, it's storing charge, then this sphere on its own also stores charge. It produces the same electric field. This electric field is unperturbed by having an outer shell. And there is a potential difference. Here the potential is 1 over 4 pi epsilon naught Q over capital R. At a distance of infinity, the potential is 0. At a distance in between, the potential is Q over 4 pi epsilon naught small r. So there exists a potential gradient from the surface of this metal to infinity, and it's because of this potential gradient. Potential gradient का मतलब difference in potential. Because of this potential difference, there exists electric field. The electric field is just the gradient of the potential, the slope of the potential. So a single sphere also qualifies as a capacitor. There's no harm in saying that a single sphere is a capacitor. Okay? So if I were to store charge on the capacitor, on this spherical capacitor, I would like to find its capacitance. I already know that on the surface of this sphere there is a potential, and I subtract from it the surface when you are at infinity, and I call this delta V. Okay? Now what is the potential at infinity? 0. What is this? This is 1 over 4 pi epsilon naught Q over R. So what is my capacitance? My capacitance is 4 pi epsilon naught R. So this is the capacitance of a spherical shell that holds charge. I just take this 4 pi epsilon naught r to the other side. I put the constant of proportionality, call it the capacitance of this system. It's 4 pi epsilon naught r. So if you look at the dome of the Van de Graaff generator, if I were to draw the dome, it was just a sphere, and it was holding charge plus Q or minus Q. Now this sphere has a capacitance which is given by this. This is, by the way, a very small number, because if this R is say 1 meter, if it's a 1 meter big sphere, epsilon is 10 to the power minus 12. So this capacitance is of the order of picofarads generally. It's really small. So the amount of charge that is held on this surface, even though the voltage can be really large, the amount of charge that it holds is really small, because Q equals C delta V. If this object is small, the amount of charge that is held on this object is also small. And you don't feel an electric shock when you touch the dome of this generator, because the charge is small, and that small amount of charge passes through your body in some amount of time. The amount of current that passes through your body is smaller than your threshold of sensation of electric current. So even though the voltages can be really large, say of the order of tens of thousands of volts, this capacitance is small, which ensures that the charge that is built up on this dome is really small. Okay, so a sphere on its own can qualify as a capacitor, and it will have a certain capacitance. Now there is another arrangement that is frequently used. It's called a coaxial system. Coaxial conductors. बड़ा अहम मैसेज आया कोई. Don't use your mobile phones in the class. You must have all seen coaxial conductors, like the cable that comes into your home, into your television. It's a coaxial conductor. It has an inner conductor and an outer conductor. Both of them are coaxial. So this is a metallic cylinder, this is a metallic cylinder. The outer cylinder is generally ground at neutral potential. This is at some high potential. So this is a coaxial cable. This is a cutaway section of a coaxial cable. A BNC cable is also a coaxial cable. Now suppose the radius of this inner conductor is A and the radius of the outer conductor, the inner radius of the outer conductor is B. And there will be some radius of the outer conductor, but we are not concerned with that at the moment. So now this is a cylinder. If I draw this in a longitudinal view, this is what the cable is looking like. This is an inner cylinder of radius A, and enshrouding this inner surface is an outer cylinder. Whose inner radius is B. So these are two long cylinders, assumed to be infinitely long, that have a charge separation. The charge per unit length on this cylinder is plus lambda, and the charge per unit length on this cylinder is minus lambda. Okay, so these are cylinders, and if I take 1 meter section of this cylinder, so this is 1 meter, the amount of charge on this inner conductor is lambda, and the amount of charge on this outer conductor is minus lambda. Okay, so it's charge per unit length, even though the charge is distributed on the surface. So now what I have is an electric field set up in this annular region. Is there an electric field? Yes, there is an electric field. शर्माई नहीं, बिल्कुल है. और electric field की क्या direction है? It's going to be radially outward. It will start on this inner surface, on this inner sphere cylinder, and terminate on the inner surface of the outer cylinder, because both of them are metallic, they are conductors. So there is an electric field. जी. ये अगर positive है, ये minus. Minus lambda is the charge on the inner surface of the outer cylinder. Okay. So now, what is the amount of this electric field? How much is this electric field? How much is the electric field? It's lambda by 2 pi epsilon naught r. So if I take a Gaussian surface, I draw a Gaussian surface that's at a radius r, which means I'm drawing a surface like this. This blue is my Gaussian surface at a radius r, length L. Okay, now for this Gaussian surface, the electric field that's it's always normal to the area vector on this Gaussian surface. So the angle between the area vector and the electric field locally is 0. So I can just take the normal product instead of the dot product. Cosine theta is 1. So the electric field, say it's ER into the total curved surface area of this cylinder is 2 pi RL equals the charge enclosed, and it just encloses the positive charge. The amount of charge that's enclosed is lambda L, which means that the electric field, which is pointing radially outward, is lambda over 2 pi epsilon naught r pointing radially outwards. Now I would like to find the capacitance of this wire, of this cable. Okay, now how do I find the capacitance? I would need to find out the potential difference between these points. Okay, as I go from A to B, what's the potential difference that I accrue? So I go from A to B, I put VB minus VA, I call it delta V, is negative of the work done by the electric forces. I'm going from A to B. This is my electric field, lambda by 2 pi epsilon naught r unit vector r dot product with dr unit vector r, because I'm going radially outwards. So this turns out to be minus lambda 2 pi epsilon naught dr by r. I'm going from A to B, minus lambda 2 pi epsilon naught. This is natural log of r. So I have natural log of RB divided by RA. Now, is this quantity positive or negative? Instead of RB over RA, I write B over A. Is this quantity positive or negative? B is greater than A, so this number is greater than 1. So what's it's positive. This is positive, but there's a negative sign here. So overall, this thing is turning out to be negative, which means that VA is greater than VB. Does this make physical sense? Yes, the potential here is greater than the potential here, because this is a positively charged conductor. So the potential here is greater, the potential here is smaller. In any case, the potential difference, its absolute value, delta V, is lambda over 2 pi epsilon naught natural log B over A. So this is the potential difference. This inner conductor is at a higher potential, this outer conductor is at a lower potential. Okay? Now I would like to compute the capacitance. This is my potential difference. Delta V, the absolute value, equals, now what's lambda? Charge per unit length. It's Q per unit length, 1 over 2 pi epsilon naught natural log B over A, which means that my Q equals Q over delta V equals 2 pi epsilon naught L natural log B over A. Now what is Q over delta V? Simply the capacitance of this system. So the capacitance depends now upon the length. You have a longer cable, the capacitance is higher. Longer cables will have higher capacitance, longer coaxial cables. And remember, this coaxial cable makes home appliances run, it makes your computers run. It's a really important system in all of electrical engineering. All waveguides, all transmission lines will have a capacitance, because there is some inner conductor and there is some outer conductor, and every transmission line acts as a capacitor. Okay, so if you look at this capacitance, I can define a capacitance per unit length as 2 pi epsilon naught natural log B over A. So if I would like to reduce the capacitance of the line, because you generally assume in engineering that all your transmission lines are just conductors, they are not capacitors. So you would like to reduce the capacitance. You can reduce the capacitance by making this quantity larger. In other words, by making B much larger than A, by having a big air gap inside the line. but that is not really desired, because if you have a big outer conductor, the volume of material that you need to use is large, and economics trickle in then. You can't have a large outer conductor because it will be very expensive to build such a wire. So this is the capacitance per unit length. Biologists know that if you have a neuron, right, which has two of these regions and an axon, and if an impulse passes across this neuron, then this neuron also acts like a transmission line, and it will have a certain capacitance per unit length. And in the next lecture I'll show you a demonstration in which whenever there is a capacitance, there is some delay in the propagation of energy. Okay, and that is why there is some delay in transferring impulses from one point in the body to the other. In any case, for a coaxial cable, this is what the capacitance turns out to be. One more example. If I have a capacitor that is storing energy, the amount of energy that a capacitor stores, U, is given by half epsilon naught E squared into the volume, right, of the capacitor. Agreed? So I can write this as half epsilon naught. Now what is E for a parallel plate capacitor, say? Sigma over epsilon naught. And in terms of the potential difference, it's, what is electric field in terms of the potential difference between the plates? Delta V divided by L. Delta V divided by L squared. And you have a volume. Okay? Now can you please express this in terms of capacitance? Is it possible to do so? Can you give it a shot? Express this in terms of capacitance. Half epsilon naught 1 over L squared. What is delta V? Delta V is Q over C. Q squared over C squared into the volume. What is the volume? It's area times length. So I can replace this volume by area times length. I come here, U equals half epsilon naught Q squared L squared. Now what is C? C is just, we have the value of C here. This is just epsilon naught A over L. So C squared is epsilon naught squared A squared L squared. And volume is area times length. Okay. Okay, this area goes like this. This epsilon naught goes like this. So I'm left with half Q square epsilon naught area over L. But this is simply the capacitance. So I'm left with Q square over 2C. So the energy stored in a capacitor is Q squared over 2C. So I have three different formulas for the energy stored in the capacitor. I can have half epsilon naught E squared. I can have half Q squared over C. I can also have half C delta V squared. All of these are equivalent and you can derive one from the other. Now, one thing that you have to do on your own is that if I have capacitors in series, this is the symbol for a capacitor. Two lines, parallel lines of the same height. So if you have capacitors in series, this is something that you already know. If their capacitances are C1, C2, C3, all the way up to Cn, then the total capacitance of this system, C equivalent, is given by this formula. It's just 1 over C1 plus 1 over C2 all the way up to 1 over Cn. So this is when capacitances are in series. I will not go into the details of this. There will be ample examples that you will see in tutorials and recitations. And if capacitances are in parallel, then the total capacitance of this system will simply be the sum of the capacitors. So this is what is meant by saying that capacitances are in parallel. In this case, the voltage or the potential difference across each capacitor is going to be the same. Because this is a metal, all of these points are equipotential points. So this point must have the same potential as this point, So all of these plates are at the same potential. But they may carry different charges because the capacitances are different. Okay? So this is something for you to explore on your own. I will not do this in a lecture. We finished our discussion on capacitances. There's a tutorial that I've prepared which has some questions on capacitance as well. I'm going to upload a homework this week that will be due on the Monday or probably the Tuesday after the break, and there's going to be our second quiz on the Friday following the break week. And the marks for the first quiz will be uploaded in probably a couple of days. And I'm going to discuss the quiz in Friday's class. Okay? See you inshallah on Friday.